Bismillahirrahmanirrahim. Assalamu alaikum viewers and welcome to my channel. And in this video, our previous video deals with the gamma function and gamma integrals, how to evaluate the gamma integral and what was the story behind that function and the relative properties and their proofs and all that. So we tried to cover all the possible aspects of our gamma function in the previous two videos, and now over here we have jumped on the second integral of that category, that is called the beta integral. Okay, so you see this beta integral that you can watch over here. This is said to be this is the integral that was studied deeply first time by the Euler, Swiss mathematician, and that's a reason why this integral was on his name, and it is still known as the Eulerian integral of the first type. You can see over here. Later on in 1990s, these three mathematicians, Legendre, Whittaker, and Watson, they just named this Eulerian integral of the first kind by the beta function of these two real numbers, L and M, which are positive indeed. Okay, so that's, you can say, that's how you can understand that beta function is the interpretation of Eulerian integral of the first kind, and this name beta was given to this integral by these three mathematicians. That's the reason why this integral was later on become famous as the beta integral, and this is something that happened in 1990s. Okay, so that's it. Now it happens that usually beta integral is represented by the Greek lowercase this beta. But instead of that, the actual representation of beta function is represented by the Greek capital beta, which is rather similar that of the Latin capital B over here. And we do not use actually this Greek lowercase, but nowadays it is lavishly used in the books, so people usually recognize beta function by this notation. But actually behind the curtain, the real story is this is the actual representation. Anyways, so this is just an additional thing. Now you see, we have just tried to cover a small introduction of beta integral, and in this video what we are going to do, we are going to establish a relationship between the beta and the gamma functions. Okay, and it involves a proper derivation here that we are going to cover in this video. Okay, and in the next video we are going to deal with the related examples and all that. So let's have a look and let's see how this beta function is related with the gamma function with respect to these two real numbers. Make sure that your L and M, let me write over here, belongs to your real number, and it should be positive. A positive real number means, in other words, you can say that L and M should be positive and greater than 0. Alright, so the beta function of these two positive real numbers is expressed by means of Eulerian integral of the first kind that you call beta integral. Okay, so now let's establish and try to understand how we relate beta and gamma functions. So this is something that we have to prove here in this video, right? So the beta function of these two positive real numbers is equal to the product of the gamma functions of individual gamma functions of these two real numbers upon gamma function of the summation of these two real numbers. So we have to show how this thing has been brought. Okay, so what we have to do, we are going to pick up our gamma integral. I'm not going to call it again and again Eulerian integral of the first kind. It takes so much time, as tongue simply stuck over there. Okay, so I'm going to pick up this beta integral. All right, and I'm going to apply my by parts strategy, and then we are going to split up this integral. Okay, so let's pick up our beta integral. And beta function is the integral of these two different types of polynomials. Okay, where L and M are, I repeat, they are the positive real numbers, and this is a very definite integral, limits going from 0 to 1. Okay, so now it is your choice. You can pick any this is the integrand, which is expressed as the product of two polynomials. One is this, another one is this. Okay, so it is your choice. You can pick any integral as your f of x, and any integral as your g of x. Okay, so I have decided to pick up this function, or this polynomial, as my f of x, the function that I have to derivate while performing my by parts, and this is something I'm going to take as my g of x, the function to be integrated while performing by parts. Okay, so let me repeat here the formula of your by parts. The integral of the integrand, which is the product of two functions, is going to be evaluated by means of this formula. In order to get aware or in order to get acquaintance with by parts, you can have a look to my videos related to the integration by parts. Okay, you can check out my playlist out there in my channel. Okay, so now let's sort out our f of x and g of x in a manual way. Okay, that's it. And my g of x is it is L minus 1. Sorry, my mistake. Okay, so now over here, first of all, let's solve this thing. We are going to take the derivative of both sides with respect to our x. So we are going to differentiate both sides with respect to our x. Okay, so we are going to differentiate, and we are going to apply here the conventional formula of the derivative of our xn, which is n times the x power n minus 1. Okay, so just take this whole thing as your base, take it as a x, and this whole power as your n. Okay, so it is going to be your n x n minus 1. It's going to be then m minus 2. Okay, so your f dash x is getting close now. Excuse me, it's just nothing but a summer virus. Okay, so let me write down over here for you that my f dash x is m minus 1 times x power n minus 2. Alright, for my support. And now let's come over here and let's integrate both sides with respect to our x. Okay, and that's how we are going to get our capital G of x. Alright, excuse me. And over here we are going to apply the formula of our integral of xn, which is xn plus 1 upon n plus 1. Alright, so you know that this whole thing is behaving as your n over here. So x power n plus 1 upon n plus 1. That's how it is happening. So what is left here? Minus 1 and plus 1 and gets cancelled. So you are having x power l upon l. Okay, plus some constant. And this is your capital G of x. Alright, so this thing, for my convenience, I can write like this, that my G of x is xl upon l. Alright, that's it. Now my f dash x and my G of x is has been so obtained. My simple f of x and small g of x is over here. We are going to put down over here in the formula. Okay, so let's see how it looks like. So I have just written these functions in an organized way, so it's going to help you out here. So now I'm going to apply my by parts formula over here in this integral. So, and make sure I have to keep my limits in mind, okay? So this is my f, this is my g according to the formula, okay? I'm going to put down my limits here. Okay. Minus integral f dash x in g of x, okay? This is my f, this is my f dash x, and this is my g of x. Okay, now over here you can see that your m minus 1 and l are the constant values, so they're going to be placed before the integral right over here. Okay, so let us organize, and in the next step we are going to apply the limits, as well as we are going to put these two constant values outside the limit, outside the integral, this integral. Okay, so once I'm going to apply my limits over here, so I'm going to remove these mods, I'm putting my square bracket out there, and now I'm going to apply my upper limit first. Okay, so at the place of my x I'm going to put down my 1. Okay, 1 power l is 1 upon l, okay, and 1 minus 1 m minus 1. Okay, this thing turns 0, then this whole thing will become 0. Minus, at the place of my x now I'm going to put down my lower limit. So 0 power l is 0 itself upon l. 1 minus 0 m minus 1. Okay, and then I'm going to write down these two constant values outside the integral. Okay, that's it. So you see this thing has been turned into 0, and this thing also gets multiplied with this 0. Both these terms will become 0, so this is now your 0. Okay, I've just encountered a mistake here while performing the differentiation over here. I have to apply the chain rule on this space at the end. I simply forgot to do that. Okay, let me rectify. I have to apply my derivative on this, my chain rule derivative on this space. Okay, so once when I apply the derivative, I'm getting -1 here. Okay, so once when I get -1, that -1 can be placed in the beginning. Okay, so this is what my f dash x is. I simply forgot to put down the chain rule. I'm sorry for that, that's my mistake. So this is your f dash x having this negative sign. All right, excuse me. All right, so I'm going to put down this negative sign over here as well. Okay, I'm going to put down this negative sign, and this negative and this negative will become positive, so I'm going to put down my positive sign here. All right, now it's just fine. Okay, so once when you put down 0 here, this will become 0, so this whole term will become 0. And once this is the 0 here getting multiplied, so that's why this whole term will also turn into 0. So as a result, this whole part will become 0, and we are having just this thing left. Okay, so let's copy this whole integral. So that's how your beta function is having a face like this after getting integrated by parts for the first time. Now still you can see that the integrand is haven't been that much simplified. So how you're going to handle this thing, I mean, you have to perish at least one polynomial present in this integrand. So how many times do you have to apply the by parts here? because you have taken this function as a function to be derivated in your first attempt out there. So you see, this was the initial form of your beta integral, and this function was taken as the function to be derivated, and this function was taken as the function to be integrated. So you see, this function or this polynomial is having this power m minus 1 over here. So if I'm willing to vanish this polynomial over here, how many times do I have to derivate? You say I have to derivate it m minus 1 times, then this polynomial is going to be vanished, because it is going to have power 0 over there in the last derivative once you take m minus 1 times. So m minus 1th derivative of this polynomial is going to be 1 then. So maybe I'm just talking this orally, so this might be passing over your head. So how about if I do one of the small example related to this discussion, and then we are going to come back to the derivation once again. So for example, if I pick up a polynomial or I simply pick up a variable having power 4 on it, okay, x power 4, just take it like that, x power 4. So let's understand through that example first, and then we move back, and then we return on this derivation, and we are going to continue from where we have stopped, and we have stopped right over here. Okay, so let's try to understand first of all with the example first. Let's take it like this. For example, my f of x, instead of taking 1 minus x power m minus 1, I'm going to take a simple polynomial, and I just take it as x power 4. Okay. Once when I take its first derivative, okay, and I'm using here this formula, which is n times x n minus 1. This is the formula that I'm using here over here. So it is going to be 4x n minus 1, 4 minus 1, and it's your 4 times x cubed. Okay, this is your f dash x. All right, this is your first derivative. Okay, now I'm going to once again derivate this function that is said to be the second derivative. Okay, I'm going to derivate this f of x, which is actually the derivative of my f dash x. Okay, so this is my 4x cubed. All right, so 4 is going to be written outside or before the operator, and it looks like this. Now once again I apply my formula of xn. It's going to be 4.3x squared. Okay, and this is something that is your second derivative represented by f double dash x. Okay, now take the third derivative of your f of x. Okay, which is the derivative of your f double dash x actually. So it is 4 into 3. I'm not writing 12 here. I have to keep these values as it is. So it's going to help us understanding the concept later on. So, and this is your x squared. That's it. Okay, now once again you apply the formula of your xn, derivative of your xn, which is n x n minus 1, and this is your 1. You are having 1 power. Okay, so it's going to be power x. All right, this is it. Now take the fourth derivative of your f of x, which is actually the derivative of this was your third derivative function represented by f triple prime x. Okay, so this is the derivative of your triple prime x. Okay. Derivative of your x, and this is going to be 1 then. Okay, so 4.3.2.1, this is what is left. That's what is left. So you see this is equal to your 4 factorial. All right, that's what is happening around. So you see, whatever the power you are having here, if you derivate this function equal to the times what the power is over here, okay, you're having power 4, you take the 4 derivatives here, and the 4th derivative will give you the answer equal to the factorial of your power. Okay, so that's how the polynomial is going to be vanished. All right, so you see, if I take the m minus, if I differentiate, if I'm having my function of this form, m minus 1, okay, and I'm just taking out the derivative of this thing, and this m minus 1, if m is a positive value greater than 0, so once when I take its m minus 1 at derivative, okay, of this function, then this function is going to get perished. All right, it is going to get finished, and it will be equal to, therefore, the factorial of the power. That's how the thing is going to happen. All right. Excuse me. So this is something that I'm going to apply over here in this step. All right, this was my first integration by parts. I'm going to apply my by parts m minus 1 times. In this way, I'm going to derivate this polynomial m minus 1 times, and it's going to get vanished, and I'm going to have this value at its place. All right, that's what is happening. And every time, in every step of my by parts, no matter how many times I'm applying my by parts, this thing is going to be converted into 0 every time. So, and just the integral form is going to be left. So this is an understood thing. You're not going to apply your integration by parts every time, showing this whole work again and again. No, you're going to generalize this thing now. Okay, so now this part has been understood. Okay, now we are going to move up to this thing, that once when we integrate this function m minus 1 time, what is going to be our answer at this place? Okay, what is going to be our answer at this place? That's what I want to know. Okay, so let us try to understand this thing as well with respect to an example. Okay, and let's see how it looks like. So let us try to understand with a simple polynomial form, and let us assume that our g of x is equals to x cubed. Okay, now once when you take, you have to now integrate it m minus 1 times. Okay, so in the previous example, we have derivated our function, this function, okay, 4 times. That's what we have done. Okay, so we are going to integrate this function 4 times as well. Okay, so once when you take the first integration, once we integrate this function for the first time, it's going to be, we are just applying the formula of our integral, which is integral of our xn is, you know well, it is this. Okay, so we are just using this formula over here. So the first integral is this. Okay, this is it. I'm not writing plus some constant every time. We're just understanding the thing, that let's go with the flow. Okay, this is your first integral. All right, now we are going to integrate this answer once again. Okay, so it is going to be x4 plus 1 upon, it is 5, it is 5.4. I'm just writing this 4 together. So this is x5 upon 5.4. all right, not 0.4 is getting multiplied. Now take the third integral. xy dx is going to be x power 6 upon 6. Let's write it directly. Okay, take the fourth integral, the last integral. It's going to be x power 6 plus 1. So it is your x power 7 upon 7.6 dot 5.4. So this is it. It's just a product of these two numbers. So now just arrange the power so that it's going to involve this power and the number of times you're integrating. So you can write like this. And it's giving you 7, okay? This is the number of times you have integrated the function. This is the original power that you used in the beginning that was present in your g of x, okay? So it is your 7 dot into 6 into 4 into 5, like that. So likewise, following this strategy, if I integrate this function, okay, if I'm having this function and I'm integrating this function m minus 1 times, all right, so what should be what do I have to write in at the power? So you see, you just write your x over here. This is your number of times you're integrating, and this is your m minus 1. This is your original power on the variable. This is your L minus 1. So it is going to be original power plus number of times you're integrating. Okay. So it is L plus m minus 2. That's what the power is going to be. And in the denominator, how you're going to handle such kind of stuff, what numbers you're going to write. So you see the first number was your 4 here, and how you obtain your 4, you just add power 1. You add 1 in the power, okay? So over here our power is L minus 1. So L minus 1 plus 1, okay? Then L minus 1 plus 2, and so on. You keep on going till L minus 1 plus m minus 1. Okay, you just keep on doing like this. So that's how you just get finally this form. It is going to be your L, it is going to be your L plus 1, and it's going to be your L plus m minus 2. All right, so this is something that you are getting after integrating this function m minus 1 times. Okay, now let's move ahead and let's go back to the place where we stopped. Let's go back over here. And for my convenience, I have just named my original Eulerian integral of first kind, what you call the beta integral, as our equation number 1. And this is something that I have to handle with the by parts. So I just applied by parts first time, I got this answer. So you keep on applying by parts on this equation m minus 1 times what form you're going to get. So you see, on integrating equation 1 by parts m minus 1 times, we are going to get something like this. This beta function is going to appear like this. You applied your by parts, and this step, in every step, this thing will turn into 0, and just an integral form is going to left. So so you see, once you were derivating this thing and you did that m minus 1 times, so you just got this thing left outside. Okay, and the integral was, once you were performing the integral on this function, you just got this thing left, and in the denominator you are having some constant values, and I'm going to write those constant values over here. That's what is left. Okay, this is something. Now I'm going to apply my simple integral on this polynomial having x power n formula. That's what I have to follow. X power n plus 1 upon n plus 1, that one. So let's apply that thing, and we are going to have a form. Okay, so once you're applying the integral, it becomes x n plus 1 upon n plus 1, and you are applying here the limits. Okay, so this is going to be your L plus m minus 1, and this is a constant value. You're going to write it outside. That's it. And over here you're going to apply the limit on this thing. Okay, you're going to apply the limit over here. The upper limit is going to give you 1 and the lower limit will give you 0. So just one answer is going to be over here. Okay, so no matter what power is there on the base 1, the answer is always 1. Okay, so that's why this whole thing will reduce into 1, and this one, when get multiplied with this, you're simply going to have this answer left. All right, so the beta integral or beta function is this. All right. So this is the form. Now what you do, how about if you just, in order to form a proper relationship between beta and gamma functions mentioned in the beginning and mentioned in the question out there, so in order to bring that form, we are going to do some modifications. So how about if I just divide and multiply this fraction by my L minus 1 factorial. Okay, dividing and multiplying is an adjustment so that the original form will be kept restored. Okay, so it can be written like this, and I can write this L minus 1 factorial in the denominator in an open form. How about like this? Okay, this is your L minus 1 factorial, right? And then I'm going to write down these values, and so on. That's it. Okay, so now you can see that you are having a product starting from 1 and ending up to this. So this is now complete. This whole product is your L plus m minus 1 factorial. I hope you agree with this. So I can write this thing. L plus m minus 1 whole factorial. Okay, so this is something that you call a gamma function if equal to. All right, and in the previous videos you have studied when you were just viewing or watching the proof of the gamma function properties out there. You studied that your gamma function of n was equal to your n minus 1 factorial. All right, so in this way, m minus 1 factorial is equal to your gamma function m. This is your gamma function L, and this is your gamma function L plus m. Okay, so in this way, it wouldn't be wrong if I just write like this. So beta function of your L comma m is equal to your gamma function of m into gamma function of your L upon gamma function of L plus m. So that's how we maintain a relationship between the beta function and the gamma functions, and that's how it is proved. Okay, so that's all for this video, and I hope that you find this video helpful, and if you really did, then I appreciate, and I'll be very grateful if you simply subscribe my channel and hit on the like and share this video as much as you can with the other learners so that others will also get helped. And in the next video, we are going to maintain another property of your beta function, and then in the third video, we are moving to the examples of it. Okay, so take good care of yourself and remember me in your prayers. Happy Ramadan al Kareem. Allah Hafiz.